Hello again. Today we will be speaking about vibration of the continuous system. Today I will show you how to deal with the governing equation of the simple continuous system like a string. Okay, it means that today we have the topic continuous system dynamics, and it will be string vibration. It will be about vibration of some simple element which doesn't have bending stiffness. It will be the thin structure which cannot carry the bending moment. Okay, and how it looks like. Okay, here we have the let's say the reference level, and here we have our deformed string, such an element. Okay, and we have some parameters of our system. We have the length, the distance between the supports L, and the parameters of that thing. It will be the density of the string, the area of the cross section, and there will be important thing, there will be initial tension of that element. Okay, and if we are talking about the dynamics of the continuous system, we are not able to apply the things like Lagrangian on Newtonian mechanics in the simple way. Okay, because generally the problem is connected with that we cannot introduce the generalized coordinates for such a case, because every single point on the reference line can be treated as an independent degree of freedom. That is why we'll have to deal with the system where we have the two domains. Time domain, that domain where we see the time evolution of the dynamics, and also we have to consider the spatial domain where we see, let's say, some description of the particular points. Okay, today we will be dealing with some function W which describes the displacement of every single point from our system. Okay, let's say now we are speaking about the point which lies on the reference level in the distance x from the first support, and the function W describes the displacement. Okay, here we have the x-axis, here we have the w-axis which describes the particular displacement. That function gives us the information about the displacement of the point which is denoted by the x. We can choose every single point from the range from 0 to L and at particular time t. We have to deal with the function of the two variables. Okay. And how to deal with the dynamic of such a thing? Firstly, we have to consider really small part of the element. The infinitesimal element. We will take the element which will be dx wide. We are taking really small element where delta x is approximately 0. It's really close to 0. Okay, and if we take such an element, it will look like that. Here we have the part of our string, and what can we say about that thing? What can we say about the static condition? If we are talking about the equilibrium condition of such a part of our continuous system, we know that here we have the tension force T at the point x plus dx and at the time t, and here we have some different value, and here we have the t at the point x and at the time t. It's the, let's say, point 1, it's point 2, point 1 is here. We are speaking about such a beginning of our segment, and here we have approximately 0.2. I mean, it's a, let's say, zoom of that part, okay? Some detail view, let's say. Okay, and it means that our coordinate frame, our reference frame, which will be here, is as follows. I mean, here we have the x position if we are talking about the distance from the beginning, and here we have the position of the x plus the x, because that distance is exactly the x. And what we see here, we see that that value, that thing, is given by the x plus dx and t. Okay, next we will introduce two forces. There will be the horizontal force, t h, let's say, at the point x plus x dx at time t, and the same situation here, th x plus dx, sorry, of course, x and t. And second thing, we have also, it's obvious, we have the vertical force, because the vertical force is given by w. I will denote that thing as a tw. I mean, we have the tw at the point x plus the xt, and second thing here we have tw at the point x and point t, which is facing downward. Okay, and let's consider the equation of the equilibrium. If we are talking about the horizontal axis, I mean, if we are talking about the x-axis, we see that the equilibrium is given by that only by that forces. I mean, we see that the th x plus dx t minus th, because we see that the force th at the point x has the negative, I mean the opposite facing to the assumed coordinate frame, and everything is equal to 0 because we don't have any vertical, any horizontal force. It means that th plus x plus delta x at the point t is equal to th at point x and t. It means that wherever we take the point of the consideration, we will get that the th at the point x plus delta x, it will be exactly the same as a th. I mean, the horizontal force is a constant, is an invariant of that problem, of that dynamic system. And because we know that we have some initial tension of the problem, it has to be equal T0, because in the initial position, our system will look like that. I mean, in the initial position, our spring will be exactly the same as a reference line, and the tension force will be exactly here. It means that even for that case, that equation has to be fulfilled. It means that every single horizontal force has to be T0. Okay, let's consider equilibrium of the W direction. I mean, let's consider the equation of the equilibrium for the vertical axis, and we see that in our case it will be given by Tw at the point x plus delta x plus, sorry, of course, at the point t, minus Tw at point x and t. And it will be equal not to 0, because our system, we are considering the dynamics of our system. I mean, we have to consider then, if we're talking about the right-hand side of our equation, we have to put the inertial force, because we have some motion about the W axis, I mean along the W axis. That is why we have to put it here, the mass of the system. I will denote that thing as a delta m, because it's a mass only of the segment, times acceleration along the axis W. Okay, and now we have to only deal with that problem. How to consider, how to find the values of particular elements. Firstly, how to compute the acceleration of our system. Of course, it will be, like always, the second derivative of displacement, because we have to, this time, we have to deal with the multivariable function. We have to use the partial derivative. That is why the acceleration will be described by such a symbol. How to find the delta n? It will be length of our segment times the area. It will be the volume of the segment of our string, and we have to multiply that thing by the density. Okay, sometimes that part can be called the linear density. Okay, I mean the wave of the 1 meter of the string. Okay, and let's put the data. I mean the numbers. It will be delta x times linear density, let's say. And now we have to deal with the TW. Firstly, we see that here we see the difference between the TW, the point x plus dx, and the point TW. We see that it's a differential of function TW, okay? I mean, we are able to express that thing as a first derivative of the TW over dx, I mean, with respect to x times delta x, such a thing. Oh, of course, I forgot about something. We see that I forgot about the acceleration. I will put it in using the red color. Oh, such a thing. I mean, we are able to express the differential of that thing as a first derivative of the TW function with respect to x times the differential of the x, because the delta x can be, if it will be small value, can be called treated as a differential of the our spatial variable. Okay, and we are able to simplify that thing. It means that here we have that the linear density times second derivative of w is equal to dTW over dx. And now we have to find what is the connection between the TW and the W. And it's easy to find because we see that we have some relationship between the TW and TH. Because if we introduce the angle between the value of the tension force, I will denote it as a alpha. I mean the tangent angle between the x and the value of the function, the same if we're talking about that thing, then we will be able to compute the value of the TW based only on the TH. And we know that the TH is exactly T0. Of course, the angle alpha will be different for the different value of the x. That is why I have to emphasize that fact. I mean, here we have the alpha of x and t. Here we have the alpha. Sorry, I have to improve myself. Here we have the alpha at the point x plus delta x and t. It's important thing because we see that here we have the different alpha angle and here we have the different alpha angle because the coordinate is different. Okay, how to compute it? We see that the TW over T0, it will be tangent of, the tan of alpha. I mean, if we are talking about the TW and the point x and t over T0, because it's the same value for every single point, we have the tangent of the alpha at the point x and t. Okay, and now we have to find, and now we see that the TW is given by the T0 times tangent of the alpha x of t, and now we have to deal with the problem how to determine the tangent of the alpha. But it's easy because we know that the tangent of the continuous function, which is given by the alpha, it's its derivative. Okay? Because we have the multivariable function, we have to deal with the partial derivative. I mean, the tw can be expressed as a t0 times tw over dx at the point x and t. What does it mean? That it means that if I put everything to my equation, I will get such a thing. I mean, it will be linear density, I mean the rho L, second derivative of w with respect to t, and it's equal to t0 times second derivative, because we have first derivative and another derivative here. It means that we have the second derivative with respect to x of w. And now at the end we can divide everything by the rho L, and we are getting the wave equation, because it's the name of such an equation given by such a formula. And that thing sometimes is called as a square of the velocity of the moving of the wave. Okay, as you see, it isn't especially complicated to find the governing equation of the continuous system. We have to deal only with the multivariable function. Thank you for attention and see you next time.